Hello, everyone. Thanks for joining. I am extremely excited today. I'm speaking to Dr. Lawrence Krauss. Dr. Krauss is the president of the Origins Project Foundation, and they're going to be having a trip to Iceland and Greenland in September of next year. And he also is the host of the Origins podcast, and he's an author. He's written books. A few of his books are A Universe from Nothing, Why Is There Something Instead of Nothing, The Greatest Story Ever Told So Far, Quantum Man, Richard Feynman's Life and Science, and The Physics of Star Trek. Hi, Dr. Chris. Thank you very much for coming on.
It's a pleasure to be with you virtually.
Well, I know you're busy, so I guess I'll get right into it and figure, I'll quote Julie Andrews here and start at the very beginning because it's a very good place to start. And I was wondering if we could start talking about the Big Bang. But before I do, I just got one small question because I was having I don't want to say an argument with a friend, but the term Big Bang, like from the way everything I've read and everything I've kind of watched about it, like there were quantum fluctuations or like an event, and then about 40 trillionths of a second later, that's when the inflation started, and that 40 trillionths of a second later, that's what's considered the Big Bang, not the event preceding it?
Well, it's semantics, of course, but traditionally I think we still mean by the Big Bang the creation of the universe, the instant when space and time itself began. So it is true that our visible version of the Big Bang, now that we think inflation happened, and it was a lot earlier than 40 trillionths of a second after the Big Bang. But anyway, that produced the observed Big Bang expansion. But the Big Bang itself, I think it's conventional to refer to that, for that to refer to the actual instant when our universe came into being.
Okay, thanks. So like starting, like going back to that. So so anything I've read about the inflation, so it's like it didn't happen evenly across, it wasn't just like smooth all the way across. So there's like still pockets of inflation going on here and other places where it stopped, or.
Well, let's see. Well, again, of course, you have to realize that inflation is still just a theoretical idea. We have lots of indirect evidence that suggests it likely to have happened, but not yet any direct confirmation. But generically, the way inflation works in most inflation models is that some region of space expands exponentially fast for some time and becomes unbelievably large. And then that period ends, and then and that energy that's stored in empty space causing that expansion is released and causes that hot, Big Bang expansion we see. But in the kind of metaspace or multiverse, that as we now call it, that expansion happens only in a limited region of what is all of space at that time, and other regions could be inflating now or later. And so in that picture, our universe, our observable universe, is just a small part of what we would call a multiverse, in which inflation is happening or has ended or is about to begin in potentially an infinite number of other places. And the interesting thing is, after inflation ends in each one of those regions, the kind of laws of physics that come out of inflation at the end could be slightly different. So our universe that we see, the product of inflation, could be one of many different regions of space, none of which we'll ever be able to communicate with, but in those regions of space which are effectively isolated universes, the laws of physics could be different.
Okay, so
if that helps, it doesn't confuse things more.
No, but because I was trying to think of it sort of like if you think of like an infinitely long sheet of bubble wrap, and as it's rolling out, like each little bubble is its own little pocket.
Well, that's true. Our universe is kind of like a little bubble in a I'm not sure, bubble wrap, but at least if that helps you, then that's fine. It didn't make a pop when we bursted, as far as even though I love bursting bubble wrap.
Yeah, I think that's a universal thing. That might be another universal constant.
Yeah, exactly.
Okay. So, since I've got you, I'm going to ask you a bunch of questions that have always kind of bugged me, so I hope you don't mind. The next is about black holes. And so, so if a star of a certain minimum size explodes, you get, incredible amount of mass, and it creates a black hole, right? Like I know
the inner part collapses,
Yeah.
and often it collapses to form what's just called a neutron star, where the nuclear physics, where it basically becomes one gigantic atomic nucleus, and stops there. But if the star is bigger than a certain size, called the Chandrasekhar limit, basically, if the inner core is bigger than a certain size, then that object will collapse to form a black hole.
Okay, like that's so when it collapses, like, because I know like the different, like, I'm gonna get this all wrong, but like, you know, the different layers of the fuel of the star goes away, right? So, but it's an implosion, not an explosion. It's
well, I mean, what happened is the star is being held up when the star is a star. There's incredible gravitational attraction of all the mass, and it's being held up against that by pressure being generated by nuclear reactions. So when the nuclear reactions stop, the gravity takes over and it just collapses. So it's basically being held up. It's like a balloon where you're constantly, we've got the mouth open and you're constantly blowing into it. The minute you stop blowing into it, the pressure from the elastic, the tension causes it to collapse. And in some sense, the star is like that. It's waiting to collapse. It's being held up against that gravitational attraction by the energy and heat generated by nuclear reactions. And when those nuclear reactions stop, as they do at a certain point in stars, then the star suddenly collapses. And as I say, it collapses normally. What happens is it entirely collapses until it becomes so dense it becomes what's called a neutron star, one giant atomic nucleus. And for many stars, that's as far as it gets. And suddenly when that collapse stops and the material in falling suddenly sort of hits a hard place, there's a shock wave that goes out and ejects all of the outer part of the star, which is all the elements that were formed during the star's life. And those elements later on become part of other stars and planets and you and I. So that's how the material that in your body and my body got here is some star exploded. The outer parts get kicked out. That's when it stops, you know, when it forms a neutron star. But if it's larger than a certain amount, and it's actually beyond the Chandrasekhar band, if it's about twice or three times the mass of the sun, then not even the nuclear reactions that normally would stop the collapse are efficient enough to do it, and the object will collapse to form a black hole. The inner part of it will collapse to form a black hole. So it just depends on how big the star is. For stars that are smaller than a certain amount, 1.4 times the mass of the sun, they never collapse. They just sort of die out like an ember and form a white dwarf. For stars bigger than about 1.4 times the mass of our sun, they actually have this supernova explosion where the inside collapses and the outside gets ejected. And for stars that are bigger than about 2 or 3 times the mass of the sun, that inner implosion, if you wish, due to gravity, just never stops. It forms a black hole.
Okay. Yeah, no, because I mean, like I said, I've read about it, and I mean, I have to be a complete layman on this, and I always thought of it as an explosion that caused a tear or something, and that, like, I knew it was like a dense hole of gravity. I knew it, like the star was. No,
it's not a tear. It's just an implosion. The black hole forms just simply because the same way a planet or a star forms, gravity is attractive, and material gets combined together, and the reason, and so when material gets combined together to form the Earth, it was gravitational attraction that caused it, but the pressure and tension in the rock in the Earth is enough to stop it from collapsing further. But eventually, if it gets big enough, those atomic physics effects, and really it's atomic physics that stops my hand from going through this table here that the computer's on, those aren't strong enough to stop it to counter gravity, and gravity eventually wins.
Okay. Yeah. All right. Next thing. Like I said, these are all weird things I've read about. I just don't understand. Entanglement.
Yeah. Well. Okay. That's a little more complicated. Yeah.
Yeah. Okay. Mm-hmm. So now, from what I understand, and I don't understand the process of it, but if you take two particles, you entangle them.
Mm-hmm.
And if you have one here, and if you can somehow get one magically to the end of the observable universe, if you see the spin on one here, like let's say it's up, that one will be down, right? And it's the inside.
Yeah, if you prepare them in a state, if you start together in a single quantum state where one particle, say, spin is pointing one direction and the other is pointing in the opposite direction, but let's say you just sort of create them in a combined state, and you don't know whether one's pointing north and one's pointing south, or one pointing east and the other's pointing west, but they're pointing in opposite directions, and you create them in that state, and then you separate them without allowing them to interact with their environment. That's really important, so that you have that quantum coherence. So it's still The thing that seems so non-intuitive is when they're widely separated, you could think of them as separate. But in quantum mechanics, you can't. As long as if they were in an initial quantum mechanical state initially when they were together, they're still in the same state. They're still part of a single state, even though they're separated. And what's really weird is that a measurement of one. See, the particles can be in many different spinning, and they're spinning in opposite directions, but the direction isn't fixed until you make the measurement. So in some sense, because quantum mechanical particles can be doing many things at the same time, the first particle can be spinning north or south or east or west, but you know that the other particle is always spinning in the opposite direction. So they're both doing many things at the same time. When you measure them, you suddenly say, oh, I've measured the spin north, and one of the particles is pointing north. Then the other particle instantaneously has to be pointing south, even though before the observation it wasn't determined not only was it not determined, but the particle literally was in what we call a superposition. It was spinning in many directions at the same time. So it seems like instantaneously when I measure one particle, suddenly at the other end of the universe, I'm affecting another particle. And it's true that that's what happens in the measurement, but it's not. The particles were always part of the same state together. So it doesn't make sense classically, but quantum mechanically it does. It's just the way the world works.
No, okay. Anyway, what I was trying to get at though is like, so when you have, because they're in the same state, so this one could be either up or down or left or right, and so can the other one. So does that mean it's like it's the probability wave itself that's connecting the two particles together? Like, how does that?
Well, there's no physical way. There's no good classical way to picture it. It's other than to think of it as being part of a single entity. They're not separate. They're not separate particles. And it's like when you pull the tail of a cat, it meows at the front. But it's in this case it happens instantaneously because they really are. If you want to think, it's not fair to think of them as two separate objects. They're really one object. And when you're measuring one aspect of that one object, it obviously affects all of the other aspects that you measure of that one object. The problem with quantum mechanics is it's not a problem. It's the way the world works, but it appears to be a problem because classically it doesn't seem to make sense. There's no classical picture that can somehow explain to you how instantaneously a particle very far away can be, the measurement of that particle can be impacted by the measurement of this particle. It seems to violate things like relativity. It seems like there's communication at a distance. It's true. It's not. You don't violate relativity. No information travels faster than light. You can show that there's no way you can use that to send a signal from one place to another faster than light. And so you don't violate relativity, but it is crazy, and it is crazy, but the world. That's the way the world is. The world doesn't have to please you, and classically, because we are large beings that sort of think classically and experience the world classically, it doesn't make sense to us when the world behaves in a way that's not classical, that's quantum mechanical, but it does.
Yeah. Okay. Well, that's one of the.
Sorry. I mean, we only probably confused your listeners rather than illuminated for them, but that's life.
Okay. I'm being very selfish here. This is all for me, so.
It's all right. You're the host. You're allowed to ask.
Okay, but the entanglement thing, like that, because I have a couple friends and speak to them there. They sound very rational people, but they believe in the law of attraction, and because of like the way you said, like you don't want to have the two of them interact with anything, right? Because if it's the observer effect, right? If you observe it, you change, and because it's so complicated, I'm trying to explain some of the stuff.
Look, it's good that you try and disabuse them of this law of attraction nonsense. Yeah. Because it's probably, quantum mechanics is misused more than any other kind of physics because it sounds so woo-woo. So all these New Age people try and make money off it. And the point is, you can't change the world just by thinking about it. Sorry, it's just not the way it works. You can change the world by thinking about it if then you act on it. Yeah. If you think about something to do and then you act on it, fine. But you can't change the world. Just thinking about the world does not make it. It does not change the properties of the world outside of you. And the notion that somehow we're connected to the universe by quantum mechanical woo-woo-ness is just not true. We're not entangled with the rest of the universe we're not in a very specially prepared quantum mechanical state, and therefore this notion that somehow the universe doesn't exist until we observe it is just not true in quantum mechanics. Quantum mechanics observations do impact upon systems, but they don't have to require conscious things. You know, a particle colliding with another particle is an observation as far as quantum mechanics is concerned. So they don't require people, doesn't require consciousness, doesn't require any of that, and so there's no way that you can quantum mechanically connect to the rest of the universe in a way that allows you to influence events, and it's just pure nonsense, and it's not. It's a misapplication of quantum mechanics.
Yeah, and one of the like I said, there's a couple of my friends who I talk about this, and I'll tweet about some of this sometimes, but he used a quote that I've used from Sagan, and like Carl Sagan was probably one of the guys who helped me leave religion, and it was from the first Cosmos episode, and when he said, we are a way for the cosmos to know itself. And they're like, oh, see here, he's talking about a consciousness out in the universe. And I'm like, I'm trying to explain to them what he was saying. But they're like, no, you see, even your hero says that there's this out there. It's like, come on.
Well, the problem with is language. Language is imprecise. Mathematics isn't. And we use terms rather cavalierly in science when we try and explain things to the public. And sometimes it comes back and bites us in some part of our body. When Carl Sagan was saying that, he's saying it's amazing that in a universe of just physics and chemistry, that a system can evolve that has a consciousness and can actually be aware of what's going on, and that's what he meant by we're one way for the universe to be aware of itself or understand itself. It is amazing that we can even have this conversation, and but in no sense is it preordained, or in no sense are we are cosmically irrelevant. The universe doesn't care about us, to a large extent is trying to kill us every day, and so we are not significant when it comes to the universe. We are it's the height of solipsism, of conceit, to assume that somehow we are central to the existence of the universe and that our thoughts and actions matter. They don't. They matter to us, but not outside us.
I know, like I said, I know you don't have a lot of time, but there's something I wanted to ask you, because there's a couple articles that came out in the last few days, and it just, it's something that bugs me. It's been bugging me for a bit. And you were an educator, and you still talk and give talks, and it's science journalism. Like there was one today. I think it was from today. It was about mathematics. So mathematicians disprove the censorship conjecture. Now, I don't understand enough higher level math. Like I got as far as like calculus, but I don't understand. That was 20 years ago or more than that. But I don't understand enough to like go and read the actual studies. But every time you see an article like that, there was one maybe a couple of weeks ago. Oh, a fifth new force has been discovered, and we have to rewrite physics.
Yeah. Well, you should be skeptical. Unfortunately, there's a lot of nonsense. I mean, it's not the journalist's fault completely. Universities try to get, and researchers try and get funding, and the universities love to send out press releases based on their work. And journalists are also desperate, and they scour the literature, and so often they make. Generally, when you read things, they're hyped beyond beyond their real significance, and look, generally the way you can do it is if you read about it in one source and that's it, and it's about a fifth new force in the universe, you'd be pretty darn sure it's some claim that has no basis, because if it had a basis, you'd hear about it all over the place. But generally, you should be skeptical, and you should ask, what's the evidence? And if there isn't evidence, why are they making that claim? And if they make the claim, does it disagree with anything else I know about the universe? And you have to do that in that modern world, because there's so much misinformation on the internet that we have to ask that about everything we see and hear on the internet. Be suspicious.
Yeah, no, but I mean, like the thing that bugs me the most about it, and I think it probably gets you more than than me would be, oh, they're going to have to redefine physics, or oh, they're going to have to redefine biology, or they're going to have to.
Yeah.
It's like, but I mean, isn't that what you're looking for, really? I mean, if you're looking for something very fundamental, you're looking for something that is going to have to redefine it, but they keep making it sound like, oh, well, see, they were wrong before.
They to be like Einstein in order so people to read about it, selling papers or getting clicks. So everything has to be made to be much bigger than it is. But even Einstein didn't redefine physics; he just extended it. The laws of Newton still worked. After Einstein, you take a ball like I'm holding right now and throw it up in the air, it comes back down, and Newton's laws described it. It's true that with relativity, we extend the domain in which we can understand the universe. With quantum mechanics, we can extend the domain downward in terms of scale. But what the biggest misunderstanding about science is that somehow scientific revolutions do away with everything that went before them, and that's just not true. The laws of physics that work today will continue to work whatever we know about the universe. They become incorporated in a larger whole. So it's true that every now and then there are remarkable breakthroughs that cause us to reassess our understanding and the way we picture what we sort of knew already, and they do cause a perspective change and a shift, but that's extremely rare. Usually science happens by baby steps. So A, it's extremely rare, and B, even when it happens, it doesn't throw away everything that went before. It just extends it.
Yeah, and okay, again, this is just me talking to friends and stuff, because I'm seeing it more and more, let's say in the last 5 to 10 years, because you get more of these articles come out, and like everyone's trying to publish an article or something, right? And well, see, they were wrong. Scientists were wrong about this. Scientists were wrong about that. It's like, okay, that's what, like, I try to explain to them that, and again, I'm not a scientist, and I'm a layman on this, but it's like the difference between falsifiability when you're trying to, I don't want to say, use the term prove because it's more of a mathematical term, but then, falsifiability versus verifiability. Like you're not trying to verify that hydrogen and oxygen, like 2 parts hydrogen, 1 part oxygen will make water. You're trying to show that it won't make anything else, right?
Or you're trying to show that supposition is wrong. You're trying to test an idea, and if it's wrong, it's wrong. And that's true that we scientists try. All science can ever prove is things are wrong. It can never prove things are right. It can prove things, absolutely right. It can prove things that some explanation works, but then around the corner it may not work anymore. So you may have to refine it. And so it's true that science evolves, but so there's lots we don't understand about the universe, and there's lots of ideas that will evolve and change. But there's some things what people don't realize is that there's a lot we do know, and what we do know isn't going to change, in the sense that a ball will fall down no matter what we learn about quantum gravity 100 years from now. Take a ball at the Earth's surface, it's going to fall down, and anything we learn is not going to change that. And that DNA is the basic block of life. And whatever we learn about the nature of genetic information or metabolism or even information content in life, the fact that DNA replicates, and that's the process by which living beings propagate not just the genetic material, by which cells and living systems reproduce. All those are wonderful discoveries, and they're never going to change. We may understand them in a bigger whole. And so I think you're right. Newspapers all the time try and say, oh, everything we thought was wrong, look at this new discovery. Well, it is true that, as I say, when I go into the office, I would be trying to prove my friends wrong rather than right, or myself wrong. Because that's how we make discoveries, by showing that some explanation we have, which is correct in one context, it actually, when you try and expand it, has to be changed to describe more things. And so we do try and prove each other wrong, which is one of the reasons why people who are suspicious of evolution, they somehow think that scientists go into a room and wear black robes and shake hands and have secret signals and say to each other, shh, don't tell anyone evolution doesn't really work. We'll just keep that secret to ourselves. The point is, if I could come up today with a paper that showed that natural selection just didn't explain the evolution of living systems on Earth, I'd be famous. So I want to be able to do that. It's not as if I don't want to prove things wrong. It's the fact that evolution survived for 150 or more years tells us, after constant tests, that the idea makes sense.
It's like I said, I try to say it to my friends, but they're like, well, you're not a scientist, and that kind of shuts me down.
Yeah, people like credentials.
Okay. Last thing, like the Origins project, because I saw that I saw you tweeted about it, and your trip to Greenland and Iceland. I'd spent 4 years living up in northern Canada, like in remote Inuit communities.
Oh wow!
And I mean, anyone who has a chance or is listening to this, try to go to it because the North is awesome. It's incredible.
It is remarkable. I obviously. I almost went up to Northwest Territories once in Canada. I've been in Alaska twice in the last few years. I was going to go up to the Northwest Territories and I didn't. But I've been in the north of Europe. I've been in the extreme north of Norway and Russia. But not. I mean, Greenland is going to be amazing to see.
Yeah, no. I mean, I loved it. I got up there and I used to work with the military and I was in Afghanistan, and we all because it was so dark out there.
Yeah.
We all bought like little Radio Shack telescopes on the base. And I got into it when I was up north. I've got a 150 millimeter telescope that I was using up north. I mean, there's no light pollution, and then
nice skies, especially. And we'll be out on a boat. And if you've ever been out on a boat at night, it's just amazing. Yeah. I have to say the sky is prettier in the south. The southern hemisphere has a nicer sky, but we'll see something in the sky, of course, that is unique to the north and the extreme south, I suppose. And that is the Northern Lights. We'll be up there at a time when you can see the Northern Lights up. I've seen them up in Canada and Alaska, but they're remarkable. And we'll be up there in October. It's the end of September and October. We should be able to get an amazing view of the Northern Lights. Besides, by the way, they're kind of Inuit-like communities up in Greenland, so we'll be able to see the culture that's there. That's of course, under threat. I mean, Greenland is like a canary in the coal mine. That's one of the reasons why we want to visit it. It's because it's melting at a rate that's exceeding any of the models, and if the Greenland ice sheet, even a significant fraction of the Greenland ice sheet melts, water levels are going to increase around the world by meters, and that's disastrous. And what we're trying to do is combine that, and I'll be talking about climate change as I will in a trip we're taking to the Mekong Delta in a couple of weeks. Another thing the Origins Project is doing, but we'll also be talking about grander ideas about how the world could be, and that's why I'm really happy that on that trip, a friend of mine who's a remarkable writer, Ian McEwan, who's written about climate change among other things in his novels, will be on the trip, as will an amazing neuroscientist, Ray Dolan, and so we'll be covering different aspects of science. So you'll be able to look at the environment and experience an ecosystem that is probably going to change potentially for maybe not forever, but for the foreseeable future. See it while you'll see Greenland while it's not green.
Yeah,
I mean, Iceland is green and Greenland is ice, but it's you'll see both of them, and at the same time we'll be talking about ideas with a remarkable group of people. So it's a wonderful combination of lectures on a variety of topics and the experience of being in the far north, which, as you say, is unique and wonderful. And I was lucky enough to go up to the extreme north of North America to see some polar bears a few years ago, and it was just an experience I'll remember forever.
Yeah, I mean, and the Northern Lights, if you've never seen them, it's one of the most unbelievably gorgeous things I've ever seen. And I was lucky where I was living in northern Quebec at this town called Kuujjuaq, and it's right in the sweet spot for where you can get the auroras. I mean, I would, in the winter, sometimes 3 or 4 times a week, and you can't
capture them very well in cameras it's awe-inspiring. It's just you really have to see it, and of course to get it well, you have to be up at the far north, because the Northern Lights happen because cosmic rays bend in the magnetic field of the Earth, and basically it protects much of the Earth from cosmic ray collisions. But when they bend, they emit light, and because of the magnetic field of the Earth, that's most concentrated in the north and the south, and that's where you see this effect most strongly.
Yeah, no, they're absolutely gorgeous. Well, I don't want to take up too much of your time. You've been very generous. Thank you very much.
Thank you.
If you want to let people know where they can follow you, I'll put all the links, everything in the description.
Sure. I mean, obviously I'm on Twitter at lkrauss1, and the podcast can be seen on YouTube and also iTunes and Patreon, but the website where you can link to it is theoriginspodcast.com. And the Origins Foundation is originsprojectfoundation.org, originsprojectfoundation.org. And that's where you can get information about the upcoming trip in September to Greenland.
All right, well, thank you very much, and thank you, everyone, for listening.